So welcome students. Today we are going to discuss about this topic, that is how to solve different differential equations by using Laplace transform. As we know that in our previous or last video on Laplace transformation, we have seen some different functions and their Laplace transformations. Now before proceeding to this particular topic, that how to solve different differential equations by using Laplace transformation, I want to show you some important theorems of Laplace transformations. Basically these theorems are needed to apply in to solve the differential equations by using Laplace transformation. And the theorems are, the first theorem, and it is also an important theorem, this is known as the differentiation theorem. Differentiation theorem, it tells us that if yt is the time domain function and capital Ys is the frequency domain function, that is, if capital Ys is the Laplace transform of yt, then by using differentiation theorem we can write that Laplace transformation of dy dt. So the Laplace transformation of dy dt, it is equals to s into ys minus y0. S into ys minus of y0, where y0 is the initial value of yt. So this is the differentiation theorem. Now let's move on to the integral theorem, and here also this integral theorem, if capital Ys is the transformation of small yt, then we can write integral, that is Laplace transformation of integral 0 to t y dt. Laplace transformation of integral 0 to t y dt, it is given as 1 by s, into ys. So these are the two important theorems of Laplace transformation. Number one is the differentiation theorem and the other is integral theorem. Now let's move on to the other two important theorems of Laplace transformation, and these are the initial value theorem and the final value theorem. Now here in the initial value theorem, if f of t and its first derivative, are Laplace transformable, then f of 0, that is the initial value of ft, that is f of 0, can be written as limit t tends to 0 f of t. So how can you find f of 0? F of 0, we can find the value of f of 0 by putting limit t tends to 0 at ft, and that is by the initial value theorem, that is equals to limit s tends to infinity s into f of s. Limit s tends to infinity s into f of s. So this is the initial value theorem. As you can see in the differentiation theorem, the second part in the right hand side, the second component in the right hand side is given as y0, and this y0 is also the initial value of yt. How you can find the value of y0? That is the initial value of yt, but just by substituting time t tends to 0 at f of t or y of t, and thus you can get the value of y0 here. So now let's move on to the last theorem, that is the final value theorem. Now the final value theorem tells us that the Laplace transform of f of t and its first derivative exist. If these two are existing, then limit t tends to infinity f of t, that is the final value of the function ft. The final value of the function ft can be given as limit s tends to 0 s into f of s. So you can see by these two theorems, that is from the initial value and the final value theorem, that these two are in reverse order. So if you want to find out the initial value of any function ft, initial value of any function ft, that is if you want to find t tends to 0 f of t, then you have to find out the value of limit s tends to infinity s into f of s. And again, if you want to find out the final value of the function ft, if you want to find out the final value of the function f of t, that is limit t tends to infinity f of t, that will be equals to limit s tends to 0, limit s tends to 0 s of s into f of s. As you can easily recall that the time function and the frequency functions are inverse to each other. So while you are putting t tends to 0, it means s tends to infinity or vice versa. So these are the four important theorems that we are going to apply while solving differential equations by using Laplace transformation. And to do so, I will show you some examples of differential equations, or rather some physical problems in which Laplace transformation is going to apply. We are going to apply Laplace transformations, and for this the first problem is a simple series LR circuit. A simple series LR circuit, that is, if you treat this, you can treat this topic in your network analysis part. So this is an LR circuit. So this is the resistor, this is the inductor, and then here a DC voltage source is given, that is V. So this is a switch. We can operate this switch by on or off. This is the resistor R, this is the inductor L. So the voltage appeared across the inductor is VL, and the voltage appeared here is VR. Okay. Now let us assume that at time t equals to 0, the switch S is closed. Now if the switch is closed, then a current is flowing through the circuit, and the circuit current can be written as a function of time, that is I as a function of t. Now by applying the KVL equation or the Kirchhoff's voltage law equation for the circuit, we can write, that is VL plus VR, VL plus VR, that must be equals to V. Okay, but now you can see from the problem itself that this V is a DC supply. This is a DC voltage supply, so it is a constant value of voltage. Every time you connect the circuit, this value will be the same. So this voltage will not be a function of time. This is not a function of time. It cannot be increased, it cannot be decreased, it always have a constant value. So while writing this equation, while writing this KVL equation, and as you know that to apply the Laplace transform, you must have a function which is either a function of time or it may be a function of frequency. But here the function itself, the voltage value is a constant voltage. So we are going to consider a unit step function ut. So this unit step function, if we product this v, if we make a product of v with this unit step function ut. Now what is the unit step function? In our last class we have shown or we have seen the Laplace transformation of this particular function, that is a unit step function, that is ut, and the value is this. Okay, so the unit step function is a function that actually has a value, while in our last class we have applied this, that this is our time axis and this is the value of ut. Now since this is a unit step function, the value is 1. Or rather, the mathematical form is ut equals to 1 for t greater than equals to 0, and that is equals to 0 while time is less than 0. So this is the unit step function. So as you can see that while time t greater than equals to 0, the function has got a value of 1. And as you can know that if we make a product of this particular function with the value of the voltage V, so this DC value or this constant voltage supply turns into a time function. So that is the reason we are going to multiply, or we are going to associate this particular unit step function with the value of the voltage, or with this voltage source V. It is okay? Is it okay? Is it okay? Have you understand why I am going to associate this unit step function of ut with our circuit, or with the voltage source of V? As because this particular circuit, in this particular circuit, as we can see that there is a voltage source V, and that V is nothing but a constant voltage source. So for applying the Laplace transform, we have to have a function which is a function of time, and if this voltage source is a constant voltage source, then we can't apply the Laplace transform. So to solve this equation by applying the Laplace transformation, we are going to associate ut, that is the unit step function, with the voltage source V. Is it okay, Pranav? So now after associating this unit step function with this voltage source, or with this value of voltage V, we have a current. We have a current of IT, that is a current which is actually time dependent, which is a current that is actually a time dependent form, that is IT. Now let us write the voltage values of VL, VR. So what will be the value of VL and VR? So now here we can also write V into ut, and then VL, that is the voltage drop across the inductor. That is nothing but, you all know that the value is L into di dt. So this is the value of the voltage appeared across an inductor. And then VR, what is the value of VR? It is nothing but IR, and that equals to V into ut. So you can see that now we have a differential equation. We have a differential equation which is a time dependent form, which has a time dependent form. Now we have to solve this differential equation. To solve this differential equation, we have to apply Laplace transformation. Now, to solve this differential equation, we just not have to apply the Laplace transformation, but we also have to apply Laplace transformation on both sides of this equation. On both sides of this equation, we are going to apply Laplace transformation. Now here, now by applying the Laplace transformation, now here we have in the first term, we can see that this is a differential value, di dt. Now initially in this particular topic, in this particular lecture, I have shown you the differentiation theorem. The differentiation theorem and the Laplace transform of the differentiation theorem. So by applying the Laplace transformation, we have L into Laplace transformation of di dt. We can write it initially this, plus capital R into Laplace transform of it, Laplace transformation of it, and then that equals to V into Laplace transform of ut. So this way you can write that we are going to apply the Laplace transformation on both sides of the equation. And now you can find out that this is, in this part we have to apply the differentiation theorem, that is Laplace transformation of di dt. I have already shown you that the Laplace transformation of the differential value, that is dy dt, Laplace transformation of dy dt can be written as s into ys, s into ys minus of y0. So from the differentiation theorem we can write it as L into Laplace transformation of di dt, that is s into is minus I0. Now what is I0? As I have told you earlier that I0 is the initial value of the current IT. So I0 is the initial value of the current, and then Laplace transformation of IT. Now what is the Laplace transformation of yt or f of t? Laplace transformation of f of t is nothing but capital Fs. Laplace transformation of yt is nothing but capital Ys. So Laplace transformation of it is nothing but equals to capital Is. So here this is capital Is. And now in the right hand side, Laplace transformation of the unit step function. In our last class I have shown you the value or the form or the Laplace transformation of 1, that is I have taken f of t equals to 1, and then I transform the Laplace, I find out the Laplace transform there, and then I have found, and you have already seen, that the value of ut equals to 1, that is the Laplace transformation will be 1 by s. So this is the Laplace transformation of ut, that is a value which is actually equals to 1. So now we have already applied the Laplace transformation here, and we have find out this particular equation. Here you can find that now if for this particular problem we are going to find out the value of it, as because this differential equation, this is the differential equation of it, or rather I. So we have to find out the value of it, but here in this particular step we have already converted the time domain function into the frequency domain form. We have already find out here from this particular step, we have already transformed it into is. So now let's take the is common. Now let's take out the is common. Now here you can find that I0 is also present. I0, that is the initial value of the current at time t equals to 0. Now before closing the switch, from this physical problem we can interpret that before closing the switch, that is at time t equals to 0, the value of the current will be nothing but equals to 0, right? So the value of I0, that is the initial value of the current for this particular equation, will be 0. So we can put I0 equals to 0, but obviously this value of I0, we have find out this value of I0 from the physical consideration of this particular circuit, as before switching the circuit on, that is before at time t equals to 0, the initial value or the value of the current at this particular circuit will be 0. So we can put I0 equals to 0 here. So the equation will become, looks like, so this equation will be now L into SIS plus R into IS, and that equals to V by S. So we can take IS common and we have LS plus capital R, and that equals to V by S. So IS, the value of IS is V by S into LS plus R. Okay? Is it okay up to this? Have you any doubts so far? Have you any doubts so far? Okay, so no doubt so far. Fine. Now, as we already know that we have to find out the value of IT, that is the current in its time domain, and we have already have the value of IS, that is the value of the current at its frequency domain. So by applying Laplace transformation, we can convert IT to IS, and by applying the inverse Laplace transform. So we have to apply Laplace transformation twice. So by applying the inverse Laplace transformation on IS, we can have the value of IT. So that is our final goal. That is our final goal, to find out the value of IT. Now, this is not actually the value of IS also, as because when you are going to apply the Laplace transformation, remember, every time you have to write the equation. You have to write the equation as the value of S plus some constant, or rather S minus, that is S plus minus A. S plus minus some constant or some value. Now here, before applying the inverse Laplace transformation to get the value of IT, just focus on this right hand side. This right hand side component, and you can find out that here we have already find out S, we have a value of S independent here, and then L into S plus R. So what I have told you, that always before applying the Laplace transformation or the inverse Laplace transformation, always put the value as a form of S plus minus A. So here S plus minus A is not here. So you have to find out, you have to write this particular part as the representation form of S plus A. Now to get this value, just we can divide this LS part by L, and if you divide this LS by L, we have only S. So that is the motto. So we have to divide this entire fraction by L in both the numerator and in the denominator part, and we will have the value of V by L, that is dividing by L, and then S plus R by L, S plus R by L. And now you can see that now my denominator part, which actually contains the S component or S part, it is actually represented, it can be represented as S plus A, that is S plus R by L. So always remember this particular part, that whenever you are going to apply either Laplace transformation or the inverse Laplace transformation, you always have to put the value, if S is present there, always S will be present while you have to apply the inverse Laplace. So before applying the inverse Laplace transformation, always put the value as S plus or minus of A. So now we have in this particular form, that is Is equals to V by L divided by S into S plus R by L. So here we can write it as simple as V by L into 1 by S into S plus R by L. Okay? Have you got it? Have you got it? Okay. So now the last step is remaining, that is, now we are ready to apply the inverse Laplace transform. And when we are applying the inverse Laplace transform, we will get the value of it. We have the value of is now. So after applying the inverse Laplace transformation, we have the value of it. But here one problem is here, as you can see, that we can't find out the inverse Laplace transformation of this particular value of 1 by S, or rather 1 by S into S plus R by L. So here there are two parts and they are in product form. So we have to split this part, and we have to write this equation as the partial fraction, and we can write it as, that is, V by L into S plus R by L. So this is the way of writing any fraction into its partial fraction form. You all know this. That is, we can write it as a constant, that is A1. Say it is a constant A1 by S plus another constant A2 divided by S plus R by L. So this is the way of writing. That is, we are going to apply the partial fractions as to break up the fraction of the right hand side, and we can write this as A1 by S plus A2 by S plus R by L, where A1 and A2 are the partial fraction coefficients. So we have to find out these values of A1 and A2. Okay. So now if this is our equation 1, this is equation 2. So now from equation 2 we have to find out the values of A1 and A2. To get the value of A1, if you simplify this part, what we get the denominator as S into S plus R by L. The denominator will be S into S plus R by L, and the numerator will be A1 into S plus R by L, A1 into S plus R by L plus A2 into S. Right? Now we want to find out the value of A1. And to find out the value of A1, just multiply these two parts. As we can see that it is written as A1 by S plus A2 into S plus R by L. Now if we multiply this fraction, if we multiply this entire part by S, only S, we have A1 by S into S, that is A1, plus A2 into S by S plus R by L. So we are going to find out firstly the value of A1 and then we will proceed to find out the value of A2. So to find out the value of A1, just multiply this with S. Okay, so we will get the value as A1 after multiplying the right hand side of equation 2 with S. We have A1 plus A2 into S by S plus R by L. And in the left hand side what we will get? We will get V by L into S plus R by L, as this S will be cancelled with the product S. So we have in the left hand side we have V by L divided by S plus R by L. So to get the value of A1, so let's remove this. So to get the value of A1, multiply both sides of equation 2 with S. Okay, so we multiply both sides of the equation with S and let S equals to 0. So what we will have in the left hand side, we have V by L divided by S plus R by L, and putting S equals to 0, we will R by L. And here we have A1 as because S is cancelled, and then A2 into S, but by putting S equals to 0, we have value 0. So now you can see that the value of A1 is V by L into R by L, so that is nothing but V by R. So now we find out the value of A1, and that is equals to V by R. Pranav, just correct your value. It will not be R by L, but the value is A1 equals to V by R. Now let's move on to find out the value of A2. Now here also we have to apply the same thing. What we are going to apply? If we multiply this equation to find out A2, so multiply it by S plus R by L. If we multiply this value with S plus R by L, as S plus R by L is here in the denominator part, so if we multiply this with S plus R by L, we have left with only A2. And then after the value, we will put S plus R by L equals to 0. That means S equals to minus of R by L. Okay, so to get the value of A2, let's multiply this with S plus R by L. To get, I'm writing here, to get A2, multiply both sides of equation 2 by S plus R by L, and put S plus R by L equals to 0, or S equals to minus of R by L. So what will happen? In the left hand side we will have V by L divided by S, as S plus R by L is cancelled. And then in the right hand side we have A1 into S plus R by L divided by S into S plus R by L, and then only A2. Now we have to put the value of s plus r by l equals to 0. If we put s plus r by l equals to 0, we will find that here we have only a2 left, and then v by l, that is s equals to minus of r by l. So let's put this value of minus of r by l, and then we have a2 equals to minus of v by r. So these are the values of a1 and a2. a1 is v by r and a2 is minus v by r. a2 is v by r. Yes, Pranav, now it is right. The values are v by r and minus v by r. Obhijit, yes, it is minus v by r. That is the value of a2. I think you have find out the value of a2, and this is correct. So now we have the values of a1 and a2. So we have already find out the partial coefficients, the values of the partial coefficients of a1 and a2. So just substituting these values, in equation 2, we can write it as a1, that is v by r into 1 by s, plus a2, that is minus of v by r. So that will be minus of v by r into 1 by s plus r by l. Okay, so we can take v by r common. And we have 1 by s minus of 1 by s plus r by l. Okay, so this way we can write, or we can break the right hand side of equation 1, and that is in the simplest form, that is 1 by s or 1 by s plus a. Now easily we can apply the inverse Laplace transform. Already in our last lecture, we find out the different values, the different Laplace transforms of different fractions or different functions. So this is v by r into 1 by s minus 1 by s plus r by l, and then by applying inverse Laplace, so by applying inverse Laplace, we get is. Is will be converted to it. So we have the value of it. Now in the right hand side, v by r will be left. Now the inverse Laplace transform of 1 by s. Initially I have shown you the transformation, the Laplace transformation of unit step function, that is the Laplace transformation of 1 equals to 1 by s. The Laplace transformation of 1 equals to 1 by s. So here 1 by s. So now we have to apply the inverse Laplace. So the inverse Laplace transformation of 1 by s will be 1. As the Laplace transformation of 1 is equals to 1 by s, so by applying the inverse Laplace transformation of 1 by s, we have 1. We have the value of 1. So that is 1 by s is converted into 1. And then again in our last class we find out the values of the Laplace transformation of e to the power minus of at. We have find out the values of e to the power minus at as well as e to the power plus at, and in that particular lecture we have find out that the Laplace transformation of e to the power at is nothing but s minus of s of a 1 by s minus a, and the Laplace transformation of e to the power minus at is 1 by s plus a. So now you can find out that this is nothing but it looks like 1 by s plus a. It is 1 by s plus a. So by applying the inverse Laplace transformation, we have the value of e to the power minus of at. e to the power minus of at, as because the Laplace transformation of e to the power minus at is 1 by s plus a, as the value of e to the power minus at. Remember, I think you must remember this value, that is Laplace transformation of e to the power minus at equals to 1 by s plus a. So here, if the value is here 1 by s plus a, so by applying the inverse Laplace transformation, we can write it as e to the power of minus, now a is here r by l, so that is e to the power minus at, that is e to the power minus of rt by l. This is e to the power minus of rt by l, and that is the way you can find out or you can solve the differential equation by applying the Laplace transformation. And as you can see from this final step, that the entire values that we have find out the value of current in the time domain form, that is it, and that in the right hand side we also have the value of the time domain function. So that is the value of v by r common 1 minus e to the power minus of rt by l. Exactly, Pranav, this is the form, this is the value, and this is the solution. So have you all understand this? Have you any problem so far? So the simplest way, if I want to give a nutshell, if I want to give you a glimpse of how to solve differential equations by Laplace transformation, initially you will find that the equation is given in its time domain form. That is the first step. Already you will find the equation is given in its time domain form, and then the first step from yourself will be to apply the Laplace transformation firstly. Now, while applying the Laplace transformation, just remember the different function values, the different transformations of different functions, and you just have to write the values here. You need not to derive the Laplace transformation of those functions. So you can just write the different functional values while transforming the Laplace, while applying the Laplace transformation. Now after that, by making some adjustments, by making some mathematical calculations, you can find out that the entire right hand side, or rather the entire equation is transformed. The entire equation is transformed into the frequency domain form. So that is the step you have obtained. After that, taking some just as here we can see that we have to find out the value. We have to find out the value of it, and already it is converted into is. So what I have done, I have taken out is, the value of is. So is, first of all, we have to find out the value in the frequency domain, the functional value in the frequency domain, and then if the functional value in the right hand side of your equation is in the form of s plus minus a, s of plus minus a, then you can just go on by applying the inverse Laplace transform. You can just go on and apply the inverse Laplace transform, but if you find the right hand side of the equation is given in not in the s plus minus a form, so you have to write it into its s plus minus a form. and after that, if you can break this right hand side into two particular fractions, either by applying the partial fraction or by yourself, then just go on and apply the inverse Laplace transform, and then you will find out the solution of the differential equation. So this is the simplest way. This is the simplest way of solving differential equations by Laplace transformation. But remember one thing, that by applying this theorem or by applying the Laplace transformation, we can only convert, we can only find out the functional value either in its time domain or in its frequency domain. Okay, so any other form of functions, any other form of differential equations cannot be solved by applying the Laplace transformation. That is a restriction, or rather you can see that is a disadvantage of Laplace transformation. But in network analysis, particularly in network analysis, every time we when we are going to find out the different current values, we by solving differential equations, we can easily apply this Laplace transformation. As you can see here, that it is a very familiar equation. It is a very familiar form of LR circuit. You have already in your undergraduate class, I think you have solved this equation. You have find out this equation by solving differential equations. But here I have applied Laplace transformation, and easily we can find out the value of the current for this particular equation. I think as already you have already mentioned that Najrul, Haradan, Uday, Jayanto, Arindam, Pranav, Madhumita, Abhijit. So all of you understand this topic. I think this is Abhijit, yes, this is known as the transient condition or the transient response. The transient condition or the transient response. In transient response, we actually apply Laplace transformation to find out the different values of the current. Okay, so now as you all understand this particular topic, I think I must stop here. And so this is the class. I am going to conclude this. I will not be available to take class on tomorrow. In our next week, I will go on to cover any other topic of your syllabus. Okay, so goodbye.